Hello, everyone. The title of my contribution on my seminar is Merging Photochemistry and Complexity Science to Promote Sustainability. Before talking about science, I want to spend a few words about my university and my city. The University of Perugia was founded 714 years ago in 1380. It's one of the most ancient universities in Italy and in the world. Currently, it consists of 16 departments belonging to the areas of natural sciences, social sciences, humanities, and technologies. It has about 26,000 students, 1,100 professors and researchers, and 1,100 staff members. But where is Perugia? Perugia is located in the center of Italy. It's roughly 200 kilometers far from Rome, and it's the capital city of the region Umbria, defined as the green heart of Italy. I show just a few examples of the beautiful green areas we have in our region. Umbria is also famous for its culinary products: truffles, chestnuts, wine, oil, cheese, ham, and so on. Specifically, Perugia is famous for chocolate, Bacio Perugina, and it was produced 100 years ago for the first time. Perugia has about 170,000 inhabitants. It's a town full of history. It has Etruscan origins, dating back to at least the 3rd century BC. There is still a majestic Etruscan arch inside our city. There are Latin monuments, such as this astonishing mosaic inside our department. And there are also medieval monuments, such as this temple and the fountain in downtown, with a civil palace behind the fountain. If you come to visit Perugia, you can also admire the beautiful frescoes painted by Il Perugino in the Renaissance era. But now I move to science, and I present the outline of my talk. I want to demonstrate that sustainable development can be promoted by photochemistry, especially when it is focused on devising effective ways for exploiting solar energy. Sustainable development can be promoted by complexity science because it investigates the behavior of complex systems. By natural computing, because it proposes effective strategies to deal with complexity. And within natural computing, artificial intelligence is particularly promising. I will talk about the case of chemical artificial intelligence, and I will present a couple of examples that ground on systems photochemistry. Finally, I will conclude and present some perspectives about the link established between photochemistry and complexity science. The General Assembly of the United Nations has proposed an ambitious sustainability program by compiling the 2030 Agenda 7 years ago. The plan proposes a program containing 17 goals to be reached by 2030. These goals regard the elimination of poverty in the world, the health and well-being of every person in the world, social justice, a worldwide economic growth that must be sustainable, actions to curb the warming of our planet, the protection of marine and terrestrial ecosystems. And there's the awareness that contributions of everyone is required to reach these ambitious goals. Photochemistry is contributing to reaching some of the goals of the 2030 Agenda. Indeed, photochemistry helps to achieve the 7th goal that concerns affordable and clean energy. Solar radiations is the largest source of energy on Earth's surface. The external layer of the terrestrial atmospheres receives 10 to 18 kilowatt hour in 1 year. And the worldwide energetic demand has been estimated to be 10 to 14 kilowatt hour in 1 year. In principle, the sun gives us much more energy than we use. Therefore, it's worthwhile carrying out research on solar energy exploitation. The solar energy arrives under the shape of electromagnetic radiations, whose frequencies are included between the ultraviolet and the near infrared. And we need to contrive smart and efficient strategies to exploit such energy. First, this energy must be absorbed and then stored as either electrochemical energy or as heat. I have contributing to the exploitation of solar energy by studying the photo-induced water splitting reaction. In collaboration with Professor Macchioni, in my department, we have investigated photocatalytic water oxidation mediated by iridium complexes. And in collaboration with some colleagues at the engineering department of my university, we have studied the synergistic effect of ultraviolet visible radiations and ultrasounds in the presence of heterogeneous catalysts to produce hydrogen from water through a sonophotocatalytic process. Our heterogeneous photocatalyst absorbs the UV and part of the visible, especially the violet and the blue region. Therefore, we have been studying the phenomenon of upconversion of incoherent light to reduce the waste of solar energy. Based on the triplet annihilation mechanism, the upconversion transforms two low-frequency photons in one high-frequency photon that our photocatalysts can absorb. It's worthwhile pursuing this research line because if we find out promising materials for solar energy exploitations, the achievement of the seventh goal will have a beneficial cascade effect on other objectives of the 2030 agenda. For example, it will contribute to the design of sustainable cities and communities. And it will reduce the emission of greenhouse gases with a consequent positive effect on the climate action. The solar energy is available everywhere, and especially in the current most developing countries of our planet. Therefore, if the economies will be based on solar energy exploitation, the inequalities between poor and wealthy countries will be reduced. The reduced inequalities will help to guarantee peace and justice among the countries. The 2030 agenda is described as a 5 Ps model regarding people, planet, partnership, peace, and prosperity. Well, we can add the sixth P, that is photochemistry. Photochemistry alone is not enough. The fulfillment of the 2030 agenda goals entails dealing with the human beings and their psychophysical well-being, human societies, world economy, natural ecosystems and urban areas, and the climate. These systems are examples of complex systems. Traditionally, they are investigated by well-distinct disciplines. And the complexity science scrutinizes complex systems through an interdisciplinary dialogue to pinpoint the features shared by all the complex systems, to propose effective methods for describing complex systems, and to look for possible new principles that rule the behavior of complex systems. The development of complexity science will help to reach the goals of the 2030 agenda and face the global challenges of the new century. All the complex systems involved in the 2030 agenda share some features. And which are these features? Well, first, all complex systems can be described as networks, whose constitutive elements are nodes and links. The nodes represent the network elements, whereas the links are the connections between them. For instance, in a cell, the nodes are the chemical compounds, and the links are the chemical reactions. In our brain, the nodes are the neurons, whereas the links are the connections among synapses and dendrites. Alternatively, in any ecosystem, the nodes are the biological species, whereas the links are the symbiotic and trophic relationships among them. Different complex systems have distinct networks architectures. For most complex systems, nodes and links are diverse and their behavior might be variable. Moreover, relationships are mutual, there are numerous feedback actions, and networks are characterized by high degrees of nonlinearity. Secondly, complex systems are out of equilibrium in the thermodynamic sense. If they involve just inanimate matter, their behavior depends on the force fields. If they include living beings, their behavior also depends on their power to use matter and energy to encode, collect, store, process, and send information to pursue their goals. Thirdly, complex systems exhibit emergent properties. A property is emergent when it belongs to the network as a whole. It cannot be attributed to a few nodes and links, but to the entire collection of nodes and relationships. Examples of emergent properties are the phenomena of temporal and spatial self-organizations and deterministic chaos. Some of the emergent properties can be interpreted by recurring to nonlinear dynamics. But there are emergent properties that are not fully understood and cannot be predicted. An example is the phenomenon of life. Life has many peculiar attributes. However, we don't know its origin. We cannot obtain life from scratch, from its molecular constituents, and we cannot predict the evolution of its forms. So the question is, why are there emergent properties that are not understood and cannot be predicted yet? Well, there are at least three primary reasons which outline an epistemological complexity. The first reason is due to the descriptive complexity. Sometimes we encounter unsurmountable difficulties in describing complex systems by using the reductionist approach, because complex systems might consist of many nodes, which might be diverse and variable in their behavior. Complex systems might consist of many links, which might be diverse and variable in time. And all these features, mentioned features, might be context dependent. In other words, some emergent properties of complex systems are variable patterns. Variable patterns are entities or events whose recognition is made difficult by their multiple features, variability, and extreme sensitivity to the context. Examples of variable patterns are the biological species, pattern and symptoms in medical diagnosis, patterns in apparently uncorrelated experimental data, a periodic time series, political, social, and economic events. It's necessary to formulate algorithms to recognize every type of pattern, whatever their context is. And the steps of pattern recognitions are data acquisition by instruments, selection of the representative features, and application of an algorithm for the classification step. Although there is a flourishing research in this field, we still need to formulate universally valid and effective algorithms for recognizing variable patterns. The epistemology of complexity, natural complexity, is also linked to computational complexity. Many computational problems regarding complex systems are solvable but intractable. Examples are scheduling, machine learning, Schrödinger equation, protein folding, traveling salesman problem, and so on and so forth. Their intractability is understandable if we consider the theory of computational complexity. In computational complexity, a problem is a computational task coupled to a question. An algorithm for solving a problem is a finite set of instructions or steps that guarantee to find the correct solutions to any instance of that problem. The steps of an algorithm can be addition, subtraction, multiplication, finite precision division, and comparison of two numbers. It's useful to determine the function that relates the number of computational steps to the size of the problem, to have an idea of the running time of an algorithm solving a particular problem. And each elementary step is performed at the same speed, or in other words, each operation requires the same amount of time that depends on the intrinsic rate of our computational machine. The size of a problem is expressed in terms of bits, n, capital letter N, required to encode an instance of that problem. And the problem is easy if it is polynomial, if the number of computational steps is a polynomial function of the size of the problem. K can be 1, 2, but never the dimensions of the problem. The class of polynomial problems is the class of recognition problems. An example of a recognition problem is track a telephone number of a person in a phone book. If n is the total number of elements in the book, the computational steps are at most equal to n. All the P problems are solvable and tractable. It's possible to determine the exact solutions in a reasonable time interval, whatever the problem's dimension. However, there exist also exponential problems, problems for which the number of computational steps grows exponentially with the size of the problem itself. These problems are intractable when n is large. Let's make an example and consider the Schrödinger equation used to answer the question, which is the total energy of a chemical system consisting of many interplaying particles? Well, the number of computational steps grows exponentially with the number of particles. When we have a system with just 500 particles, I say just because a macroscopic system consists of an Avogadro's number of particles. Well, for a system with just 500 particles, the number of computational steps is so huge that even if we have the fastest supercomputer in the world, which nowadays is the Japanese Fugaku, reaching the astonishing computational rate of 442 petaflop per second. 1 petaflop corresponds to 10 to 15 floating point operations per second. Well, even with the Japanese Fugaku, solving the Schrödinger equation for 500 particles is unreasonable because the time required for finding the exact solutions is so long, to the tune of 10 to 125 years, that is much, much longer than the age of the universe, estimated to be 40 billion years. Clearly, we must abandon the idea of finding the exact solutions of large exponential problems if the only possible algorithm is that of brute force. Therefore, we are forced to transform the original exponential problem in problem of recognizing acceptable solutions generated non-deterministically and in a reasonable time interval. In other words, the exponential problems are changed into non-deterministic polynomial problems, or NP problems. Within the set of the NP problems, there's a subset called NP-complete. It contains problems such as the Schrödinger equation, the traveling salesman problem, protein folding, and so on. The NP-complete set embodies the secret of computational intractability, since a polynomial time algorithm for one of them would immediately imply the tractability of all problems in the NP. This would mean the NP problems can be transformed in polynomial problems. The Clay Mathematics Institute in Cambridge has named P versus NP as one of its millennium problems. And it offers $1 million to anyone who provides a verified proof that either the NP problems are reducible to polynomial problems or this reduction is impossible. If the relation NP equal P were demonstrated to be true, then, as the same Gödel said in a letter to von Neumann in 1956, that discovery would have consequences of the greatest magnitude. Our life would not be the same. Everything would be much more efficient. The transportation schedules of all farms would be optimized, allowing people and goods to move quicker and cheaper. Manufacturers and business persons would improve their production processes and increase profits. It would become much easier to find new effective treatments for incurable diseases, make weather forecasts, and predict catastrophic events and the trends of stock markets. Even if one day someone demonstrated that all the exponential problems are reducible to polynomial problems and universally valid and effective algorithms for recognizing variable patterns were formulated, well, certain limitation in predicting the behavior of complex systems would remain. As far as the microscopic world is concerned, the Heisenberg uncertainty principle holds. The uncertainty principle shatters the deterministic dream of describing the dynamics of the entire universe, starting from the description of its microscopic particles, because this principle fixes an unsurmountable limit in determining accurately and simultaneously two relevant features of any particle, such as its position and momentum. We might think of limiting the description of complex systems at the macroscopic scale, neglecting their microscopic constituents. However, complex systems can exhibit chaotic dynamics, and chaotic dynamics are aperiodic and extremely sensitive to the initial conditions, and unpredictable in the long term by definition, because any determination of the initial conditions is always affected by unavoidable uncertainties. In summary, the reasons why we find unsurmountable difficulties in describing and predicting the behavior of complex systems are descriptive complexity, computational complexity, and the intrinsic limitation of the predictive power of science. Being aware of these limitations that define an epistemological complexity, how can we reach the goals of the 2030 agenda and face any other global challenges that this century can reserve us? Well, first of all, we need an interdisciplinary approach in both the research and teaching. The formation of truly interdisciplinary research groups should be favored by public and private funding. Interdisciplinary courses on complex systems should be offered within the universities. I'm participating in a European project of strategic partnership Erasmus+, whose aim is to enhance higher education on complex systems for promoting sustainable development. It's urgent to propose interdisciplinary courses on complex systems, teach the theories that have some transdisciplinary features, breaking down the traditional disciplinary boundaries, and present the properties of complex systems. This is what I propose at my university. And for my courses, I have written a book titled Untangling Complex Systems, a Grand Challenge for Science. In my book, I present the properties of complex systems by dealing with subjects of chemistry, physics, biology, ecology, economy, and philosophy. As Professor Whitesides declared in his recent essay published in Angewandte Chemie, chemistry itself is living a period of change, we are moving from an era focused on molecules and reactions to one in which manipulations of systems, of molecules and reactions, will be essential parts of controlling larger systems. Moreover, we are now completely aware that chemistry is at the heart of human and animal health, biological environment, and physical environment. Chemistry must embrace being a science for the benefit of societies. When we investigate complex systems, we cannot trust just in the reductionist approach. We also need a systemic approach to deal with emergent phenomena. Moreover, when we study complex systems, we cannot trust in a cornerstone of the original scientific method, which is the reproducibility of our experiments. Often, our experiments regarding complex systems are historical events. In this regard, the image that the philosopher Karl Popper has proposed in his essay, titled Of Clouds and Clocks, is particularly effective. In the past, science had been occupied with clocks that are simple deterministic systems having reproducible behaviors. Now instead, science has to deal with clouds that are complex systems having unique and hardly replicable behaviors. The investigation of complex systems requires monitoring the complex systems continuously because their behavior is rather highly dynamic. Therefore, it's necessary to collect, process, and store massive data sets, the so-called big data. Furthermore, it's becoming evident that an alternative way for doing experiments on complex systems is to perform numerical simulations. For these two last reasons, it's necessary to speed up our computational machines, extend their memory space, and contrive always more effective algorithms. I think there are two relevant strategies to succeed in these goals. The first strategy consists in improving current electronic computers. Electronic computers are based on the von Neumann architectures, wherein the memory storing both data and instructions is physically separated by the central processing from the central processing unit. And the pace of computers' improvement has been described by the Moore's law, stating that the number of transistors per chip doubles every 2 years. By increasing the number of transistors per chip, the number of computational steps that can be performed at the same cost grows. However, Moore's law will stop holding sooner or later because transistors will be made of a few atoms. Chips producers invest billions of dollars in contriving computing technologies that can go beyond Moore's law. The second strategy is the interdisciplinary research line of natural computing. Researchers working on natural computing draw inspiration from natural phenomena to propose new algorithms, new materials and architectures to compute, and new methodologies and models, and possibly a new theory to interpret natural complexity. Natural computing is based on the rationale that any distinguishable physico-chemical state of matter and energy can be used to encode information. And every natural transformation of these states is a kind of computation. Within natural computing, there are two important research programs. The first one exploits the physico-chemical laws to make computations. Every physico-chemical law describes a causal event, and any causal event can be conceived as a computation. In fact, the causes are the inputs, the effects are the outputs, and the law governing the transformation is the algorithm of the computation. The second research program of natural computing mimics the features and performances of the natural information systems that belong to living beings. We might mimic living cells, the so-called biomolecular information systems. We might mimic neural information systems, immune systems, and the societies. All these systems are capable of exploiting matter and energy to encode, collect, store, process, and send information. Currently, my attention is focused on the neural information systems. The human nervous system, which has human intelligence as emergent property, is significant when facing complexity. Human intelligence allows us to handle both accurate and vague information, computing with numbers and words. Human intelligence allows us to reason, speak, and take rational decisions in an environment of uncertainty, partiality, and relativity of truth, when the incompatibility principle holds. As the complexity of a system increases, accuracy and significance become almost mutually exclusive characteristics of our statements. Finally, human intelligence allows us to recognize quite easily variable patterns. Therefore, it's worthwhile studying human intelligence and trying to reproduce human intelligence by developing artificial intelligence. Artificial intelligence is revolutionizing our lives and societies. It's applied in basic and applied science, medicine, economy, and security, and well-being. There are two strategies to develop artificial intelligence. One strategy consists in writing human-like intelligent programs running in computers or special-purpose hardware. The other is through neuromorphic engineering. In neuromorphic engineering, surrogates of neurons are implemented through non-biological systems, either for neuroprosthesis or to design brain-like computing machines. Surrogates of neurons can be implemented through specific solid materials in hardware, and such hardware can be rigid if made of solid inorganic compounds, or flexible if based on organic films. Alternatively, surrogates of neurons can be implemented in wetware through solutions of specific nonlinear chemical systems. Finally, there's the possibility of using hybrid electrochemical systems. In our group, we are working mainly on wetware, and we propose the use of molecular, supramolecular, and system chemistry to mimic some performances of human intelligence and develop chemical artificial intelligence. Specifically, we are devising modules for futuristic chemical robots. A chemical robot is thought of as a molecular assembly that reacts autonomously to its environment through molecular sensors. It makes decisions by its intrinsic artificial neural networks and performs actions upon its environment through molecular effectors. The intelligent activities of a chemical robot should be sustained energetically by a metabolic unit. Chemical robots should be easily miniaturized and implanted in living cells to interplay with the cells or organelles for biomedical applications. They should become auxiliary elements of the natural immune system. So far, we have devised sensory modules. For instance, recently, we have implemented a biologically inspired photochromic physiologic system that extend human vision from the visible to the UV. We are contributing to the implementation of artificial neural networks. We propose specific chemical systems to mimic neural dynamics and investigate phenomena of temporal synchronizations through optical communication. We are also proposing the use of molecular, supramolecular, and system chemistry to implement fuzzy logic, which is a good model of human ability to compute with words. Finally, we are developing effector modules, for instance, an artificial gland that is a composite system made of a pH-sensitive hydrogel and a dialysis membrane. To succeed in our project, we follow a methodology that has been proposed by the cognitive scientist Gallistel and King and the neuroscientist Marr, as an effective methodology for dealing with any complex system. Such a methodology requires an analysis of a complex systems at 3 levels. The first is the analysis at the computational level, and it consists in describing the inputs, outputs, the computations, and the logic of the system. The second is the analysis at the algorithmic level, and consists in formulating algorithms that might carry out the computations we have found in the previous level of analysis. Finally, the third is the implementation, the analysis at the implementation level. It consists in searching for mechanisms implementing the formulating algorithms. The first example that I want to tell you today regards the implementation of biologically inspired photochromic fuzzy logic system that extend human vision from the visible to the UV. We started by analyzing the first elementary steps of human color vision at the computational and algorithmic levels. Our visual sensory system has a hierarchical structure. At the molecular level, it consists of 4 molecular switches that are 4 photoreceptor proteins having the same chromophore, that is the 11-cis retinal, but with distinct absorption spectra due to the different amino acidic composition of the pocket embedding the chromophore. At the cellular level, we have a collection of 4 different sensory cells, and every cell contains many replicas of one particular molecular switch. Finally, at the organ level, we have many replicas of the different types of sensory cells distributed on a tissue that is the retina, located within the sensory organ, which is the eye. A kind of photosensitive cell, the rod, is spread on the periphery of the retina, and it works in the presence of scatter light for the black and white vision. The other 3 types of photoreceptor cells are located in the fovea, which is the center of the retina, and they work under daylight, allowing to distinguish colors. The multiple information of a light stimulus, that means its modality or spectral compositions, intensity, spatial distributions, and time evolutions, is encoded hierarchically. And the mechanism of encoding such information can be rationalized by invoking the theory of fuzzy sets and fuzzy logic. The engineer Lotfitzadeh proposed the theory of fuzzy sets and fuzzy logic. Fuzzy logic has been defined as a rigorous logic of vague and approximate reasoning. Fuzzy logic is based on the theory of fuzzy sets. A fuzzy set is different from a classical Boolean set because it breaks the law of excluded middle. In fact, any item may belong to a set and its complement at the same time. An element may belong to any set with the same or different degrees of membership. And the degree of membership of an element of a fuzzy set can be any real number included between 0 and 1. Let's make an example. Let's think about the set of the days of the weekend. The classical description of this set will include only Saturday and Sunday. And the weekend starts at midnight on Friday and stops at the midnight on Sunday. But this description is not realistic. A better description is given by the theory of fuzzy sets, whereby even Friday belongs to the set of the days of the weekend, but with a different degree of membership with respect to Saturday and Sunday. Fuzzy sets can have different shapes. They can be sigmoidal, Gaussian, triangular, to cite a few. How does fuzzy logic model the way we compute by words? Well, in fuzzy logic, any nonlinear cause and effect relationship is described by a fuzzy logic system. The construction of a fuzzy logic system requires 3 fundamental steps. First, the granulation of all the variables in fuzzy sets. The number, position, and shape of the fuzzy sets are context dependent. Then, second, the graduation of all the variables. A word, often an adjective, labels every fuzzy set. And third, the relationships between input and output fuzzy sets are described through the syllogistic statements of the type if-then, called fuzzy rules. The if part is the antecedent and involves the linguistic labels chosen for the input fuzzy sets. The then part is the consequent and involves the linguistic labels chosen for the output fuzzy sets. When we have multiple inputs, these are connected through the and, or, and not operators. In the human color vision, the absorption spectra of the chromophores belonging to the cones are like three fuzzy sets that granulate the visible spectral region. When monochromatic radiations hits our retina, it activates the three chromophores at 3 different degrees. In other words, it belongs to them at different degrees. The modality of a light stimulus is encoded as degrees of membership of the radiation to the 3 molecular fuzzy sets. The modality is encoded as fuzzy information at the molecular level. Each cone contains many replicas of one photoreceptor protein, lights with the same spectral compositions, but different intensities excite different amounts of proteins. In other words, these luminous stimuli having the same spectral compositions but different intensity belong to the single cells at different degrees. So the intensity is encoded as degrees of membership to the cellular fuzzy sets. In other words, intensity is encoded as fuzzy information at the cellular level. Finally, the spatial information of the stimulus is encoded as degrees of membership to the spatially organized cellular fuzzy sets. The spatial information is encoded as fuzzy information at the tissue level. The overall information will be a composition of fuzzy information encoded hierarchically. It will be a matrix of data reproducing the array of photoreceptive cells on the retina. And each term of this matrix will be the product of fuzzy information encoded at the molecular level and cellular level. It's a function of the photochemical quantum yield for the photoisomerization of retina, which is the first step in human color vision, and it's a function of the absorbance of the retina at the different wavelengths into the visible. To check if this description, if this algorithm is a good description of how we distinguish colors, we need to implement such algorithm. And for its implementation, we use direct thermally reversible photochromic compounds. I show you an example of a direct thermally reversible photochromic compound. It's a spiroxide that absorbs just in the UV, so its solution is uncolored in the absence of any radiation. And if the spirocarbon oxygen bond is broken by irradiating with UV, and we obtain a photomerocyanine. The merocyanine also absorbed in the visible. Its solution is colored, and the merocyanine is thermally unstable at room temperature. If we discontinue the UV radiation, the color bleaches at room temperature. And if we record how the absorbance in the visible, for example, at this wavelength, changes over time, we see that upon UV radiation, it grows exponentially up to reach a plateau that corresponds to the photostationary state, and it remains constant unless we discontinue the UV radiation. If it is the case, we have the bleaching kinetics, that is an exponential decay. So this is the differential equation describing the coloration stage, and this is the differential equation describing the bleaching process. From the differential equation describing the coloration stage, we can infer the parameters that influence the absorbance values achievable in the visible region at the photostationary state. Such values affect the features of the color, which are hue, saturation, and brightness. And these parameters are the intensity of the UV, the absorption coefficient of the uncolored form, the absorption coefficient of the color form, the quantum yield of coloration, and the bleaching kinetic constant. My collaborator, Professor Mark Heron from Huddersfield University, synthesized 5 thermally reversible photochromic compounds, 4 chromines and 1 spiroxyl. Each one has its absorption profile in the UV. And the absorption bands of these compounds are like fuzzy sets. They granulate the UV. It's reasonable to assume that each compound has 3 distinct bands or transitions for the 3 UV regions. Each compound gives rise to a specific band in the visible region. Compound 1 produces this band centered at 610 nanometers and originates a blue color. Compound 3 an orange color. Compound 4 a yellow color. Compound 2 a pink color, and compound 5 a magenta color. The absorption bands of the color forms granulate the visible region of the spectrum. We determine the photochemical quantum yields of coloration for each compound by distinguishing the 3 UV regions. For the UVC, we consider just the wavelengths included between 250 and 280 nanometers. We also determine the lifetimes of the color forms. They last a few tenths of seconds. The final steps is the design and preparation of mixtures of these photochromic compounds with the aim of obtaining a system capable of distinguishing the 3 UV regions by giving rise to distinct colors. I tell you the criteria used for the design of these photochromic systems. First, the absorption bands of the uncolored forms are input fuzzy sets. The absorption bands of the color forms are output fuzzy sets. The equation describing the degree of membership of the UV radiation to the input fuzzy sets of the eye photogram is formally equivalent to the equation used to describe the way we distinguish colors through the cones. Then we need an equation to describe the activation of the output fuzzy sets, which are the bands of the color forms. And this equation depends on the absorption coefficient of the color form, its bleaching kinetic constant, and also the degree of membership of the UV to the input fuzzy sets. Finally, to predict the color generated by a system with more than 1 photochromic compound, we need to sum the contributions of the activations for each photochromic species. Based on these criteria, we found that all ternary, quaternary, and system with all 5 photochromic compounds effectively distinguish the UV frequencies. I show you an example that is this following bifold system containing compounds 1, 2, 4, and 5 at a concentration that you can read on the slide. When the system, such a system is irradiated by frequencies belonging to the UVA, the solution becomes green. Under UVB, it becomes gray. And under UVC, the solution becomes orange. The spectra recorded at the photostationary state, shown as the dash gray traces, are accurately predicted by the equations that I showed you before, and the calculated spectra are the red dash traces. The performances of the biologically inspired photochromic fuzzy logic system investigated in acetonitrile solutions can be extended to solid support made of cellulose. We immerse small pieces of paper in a solutions with the beadful components. We dry the paper, and then we obtain a paper having the emergent property of distinguishing the UV regions by producing different colors. It's possible to write on this paper using in green by using UVA, in gray by using UVB, and in orange by using UVC. And when the UV source is turned off, the writing slowly disappears in roughly 30 minutes. So I like now to make some comments on these first examples of chemical artificial intelligence. The beadful systems I have implemented are instances of systems photochemistry. A system of properly chosen photochromic compounds shows the emergent property of distinguishing the UV regions by generating different colors. These systems have been obtained by following the three-step procedure based on an analysis of human color vision at the computational, algorithmic, and implementation levels. The performances of our default systems can be improved. A better granulation of both UV and visible regions through the synthesis of other photochromic compounds can surely increase the discriminating power of the default system. But now I move to a second example regarding chemical artificial intelligence. And I want to tell you our contribution to neuromorphic engineering by implementing optical communications between our artificial neural models. We started with an analysis of neurons at the computational and algorithmic levels. Neurons are the fundamental cells of our nervous systems, and every neuron receives signals through its dendrites. It encodes information in the value of its transmembrane electric potential, and it sends signals to other neurons through its synapses. And the computational power of a neuron relies on its dynamical properties. Neurons are nonlinear dynamic systems that can work in different dynamical regimes, for example, in tonic excitable regime. This means that in absence of any perturbation, a tonic excitable neuron remains in its hyperpolarized state indefinitely. Such a state is characterized by negative transmembrane potential. And if such a neuron receives an inhibitory signal, it maintains its hyperpolarized state. On the other hand, if it receives a pulse excitatory signal that is so strong to push the transmembrane electric potential above a threshold value, then the neuron fires an action potential. It jumps from the hyperpolarized to the depolarized state, and then it recovers the initial state in a few milliseconds. If such a neuron receives a continuous excitatory signal, it responds by firing a train of action potentials. And the frequency of spiking depends on the intensity of the signal. But a neuron is in phasic excitable regime when it responds in analog manner to a continuous excitatory signal without firing action potentials unless it receives an extreme and short excitation. Some neurons work in oscillatory regime and fire action potentials periodically. They are the so-called pacemaker neurons. Finally, some neurons are in the chaotic regime and fire action potentials aperiodically. The pacemaker and chaotic neurons respond to external stimuli by changing their frequency of spiking. We exploit system chemistry and system photochemistry to implement artificial neural models that mimic the neural dynamics. Real neurons encode information in the value of the electrochemical transmembrane potential. Our artificial neural models encode information in the UV visible electromagnetic radiations they transmit and or emit. An example of artificial neural model in oscillatory and tonic excitable regime is the Orban reaction. The overreaction is an oxidation of thioethanate by hydrogen peroxide in the presence of copper as catalyst to obtain sulfate, ammonium ion, and bicarbonate. If we add luminol, the reaction fires chemiluminescent blue flashes of light periodically, if it is in oscillatory regime. Alternatively, we use the Belousov-Zapotysky reaction, which is a catalyzed oxidative bromination of malonic acid in a strongly acidic aqueous solutions. When the catalyst is cerium, we observe large transmittance oscillations in the UV region. The UV transmittance is low when we have cerium-4, whereas it is high when we have cerium-3. And when a solution of DBZ with cerium ions as catalyst is irradiated by UV, the solution transmits transmits an oscillatory UV signal, whose period of oscillations is equal to the intrinsic period of the chemical oscillations. In the presence of ferroin, as the catalyst, we record the transmittance oscillations in the visible region, and the color of the solution switches from red to blue and back to red. The VZ with ferroin transmits a visible signal that is modulated in intensity. When the catalyst is the ruthenium trace bipyridine, the reaction becomes photosensitive. The oscillations are detectable in the visible because the color of the solution changes from orange to green and back to orange. The catalyst is also a source of chemiluminescent flashes of red light, which are emitted periodically. Examples of artificial neuron models in phasic excitable regime are the photochromic and luminescent compounds. They respond to excitatory signal by becoming color or by emitting light. And when they receive a stationary excitatory signal, they respond in analog manner. They relax to the original state after discontinuing the excitatory signal. And the recovery of the initial state requires tens of seconds in the case of thermally reversible photochromic compounds, whereas it requires a few nanoseconds in the case of the luminescent compound. As a dynamical model of chaotic neurons, we use the hydrodynamic photochemical oscillator. The hydrodynamic photochemical oscillator consists of a solution of a direct thermally reversible photochromic compound. The photochromic solution is UV radiated not uniformly, like in the previous cases, but only at the bottom of the cuvette. And the UV radiation generates the color form and simultaneously warms the bottom part of the solutions. The solution is maintained in a cup cuvette, and the partial evaporation of the solvent induces a cooling effect at the top of the solution. A vertical thermal gradient of the order of tens of degrees Kelvin, which is stationary within the time range of the experiment, promotes convective motions of the fluid. The hydrodynamic convective flow of the solvent, combined with the thermally reversible photochromism, generates color hydrodynamic waves, as you can see on this sequence of snapshots. And these hydrodynamic waves spreads the photochromic species at the velocity of 2 millimeters per second. Moreover, periodic oscillations of the transmittance values in both the visible and UV regions can be recorded, as you can see. And these time series are actually chaotic. Photochromic compounds are also used for the design of brand new photochemical oscillators that can play as pacemaker neuron models. Through numerical integration of nonlinear differential equations, we have found that it's possible to obtain photochemical oscillations if we combine two thermally reversible photochromic compounds with peculiar spectral and kinetic properties. The two photochromes must compete in absorbing light. One of them should react photochemically and thermally quicker than the other. One is an eager beaver and the other is lazy, a lazy photochromic compound. Then we achieve an oscillatory regime that in principle can last forever within a closed chemical system, differently from what happens with the other known oscillatory chemical reactions, such as the Belousov-Zhabotinsky reaction. It lasts forever only in an open reactor. Although these photochemical oscillators are really attractive, they have not been implemented yet. What can we do with the artificial neural models that are now available? Well, we can investigate their mutual optical communication. In our brain, the effect of communication is neural synchronizations. In fact, our brain is a time machine. And when the communication involves neurons with the same intrinsic period, then we can have a synchronizations in phase, when the phase difference is 0, or out of phase, when two neurons fire action potentials with a phase shift And we can have anti-phase synchronizations when the phase difference is 0.5. When the communication involves neurons with different intrinsic periods, well, phase-locking synchronization conditions are possible. At the cerebral level, neural information grounds on a code of spatiotemporal synchronization patterns and phenomena. This code depends on the architecture of the neural networks. Within the complex neural networks of our brain, we can find 2 neurons and 3 neurons motifs. For example, 2 neurons and a unidirectional flow of information, or 2 neurons and a circular flow of information with feedback. We can have 3 neurons organized in a feed-forward neural network, wherein the flow of information is unidirectional. Or we can have 3 neurons organized in a recurrent network where there are feedback actions. To implement artificial 2 neurons and 3 neurons motifs, we have devised 3 communication architectures with the UV visible radiations as signals. In the alpha architecture, the transmitter and the receiver of the communication are in the same cuvette and in the same phase, possibly with one component segregated by micelles or nanocapsules. In the beta architecture, the transmitter and the receiver are in the same cuvette, but in 2 immiscible phases, for instance, water and an ionic liquid solvent. In the gamma architecture, the transmitter and the receiver are in 2 distinct cuvettes. The networks have been obtained by upgrading or hybridizing the alpha, beta, and gamma architectures. First, I'm going to show you examples of linear communications involving 2 artificial neural models and 1 optical signal. The sender is always in oscillatory regime, and it mimics a pacemaker neuron. The receiver is usually in its excitable regime. We always establish a master and slave relationship, although with different characteristics depending on the receiver. The first example regards the communications between the BZ reaction with the cerium ions as catalyst and the fluorophore that is the acridinium salt, shown here. The transmitter and the receiver are in the same cuvette, but the fluorophore, the acridinium molecules are protected within sodium dodecyl sulfate micelles from the harsh chemical environment of the BZ reaction. A continuous UV radiation going through the BZ reaction is transformed in a periodic signal due to the oscillations in the transmittance generated by the BZ reaction. And this modulated UV signal is absorbed by the fluorophore. And the fluorophore starts to emit a green fluorescent that is modulated in intensity and is synchronized in phase with the UV signal transmitted by the BZ. The synchronization is perfectly in phase because the relaxation time of the emission from the fluorophore lasts a few nanoseconds. Analogously, we can establish a master and slave relationship between a BZ reaction and a thermally reversible photochromic compound through the beta architecture. The BZ reaction sends a periodic excitatory signal to the photochrom, whose absorbance in the visible synchronizes out of phase with the transmitted UV signal. And this out of phase synchronization is due to the slow bleaching process of the photochrom. The slower the bleaching process, the more significant the phase difference. When the receiver is in oscillatory regime, which involves the photosensitive BZ reaction with the ruthenium-3b pyridine as catalyst, well, the success of the communication is demonstrated by the achievement of a phase-locking condition. The BZ reaction with cerium ions has an intrinsic period of 45 seconds, and it sends an excitatory UV signal to the BZ reaction with ruthenium-3b pyridine as catalyst, having 15 seconds as its intrinsic period. Well, after a while, we see that we establish a 3-to-1 phase-locking condition as the final output of the optical communications. Now, I want to show 2 examples of feed-forward neural networks based on 3 artificial neural models we have implemented. In such networks, there is, as I told you, a unidirectional flow of information. The first example was implemented to obtain an out-of-phase synchronizations between the UV signal transmitted by the Bisis reaction and the green light emitted by the acridinium salt. To achieve this goal, it suffices to introduce a slow intermediary in the optical communication. The feed-forward network is a hybrid of beta and gamma architectures. The Bisis reaction transmits an excitatory UV signal to the photochrome that is contained in the semi-cuvette by the salt in the immiscible ionic liquid. And we observe an out-of-phase synchronizations between the UV transmitted by the Bisis and the visible signal generated by the photochrome, the color form of the photochrome. Then a blue light crosses the solution of the photochrome and is transmitted as a modulated visible signal that is sent to a second cuvette containing the acridinium salt. The green light emitted by the fluorophore is perfectly in phase with the blue intensity transmitted by the photochrome, but the green light emitted by the acridinium salt is out of phase with respect to the UV signal sent by the Bisis due to the slow response of the photochromic compound. So we achieve our goal. The second feed-forward network that I show you is an upgrade of the gamma architecture, because there are 3 artificial neural models that work into 3 distinct cuvettes. Specifically, we have 2 urban reactions characterized by 2 distinct periods due to their different chemical compositions. And they send chemiluminescent excitatory blue flashes of light to the fluorescent acridinium salt contained in a 3rd cuvette. There's a trivial energy transfer from a radiative energy transfer from the 2 urban reactions to the acridinium salt. And the acridinium salt gives rise to a periodic green emission that is a convolution of the 2 excitatory signals, S and L, which stands for the short and long periods of the 2 urban reactions, respectively. This feed-forward neural network is an implementation of a 2 masters and 1 slave relationship, and it's worthwhile noticing that it's powered only by chemical energy. It doesn't require an external lamp to be sustained. Now I show 2 examples of recurrent networks with 3 neurons models. A network is recurrent when there are feedback actions. In both cases, these 2 recurrent networks that I'm going to show you involve 1 oscillatory Bisis reaction with cerium ions as catalyst and 2 photoexcitable artificial neural models. And both recurrent networks are hybrids of gamma and alpha architectures. The Bisis reaction sends a modulated UV signal to a solution containing the acridinium salt and this photoreversible photochromic compound. The UV signal is excitatory for both artificial neural models. The UV signal induces the fluorescence, the green fluorescence of the acridinium salt, and we see here the emission, the band, but also the UV signal induces the coloration of the photochromic compound. Between the 2 artificial neural models, the acridinium salt and the photochromic compound, there's a reciprocal negative feedback action. The photochromic transformation from the colorless to the color form inhibits the fluorescence of the acridinium salt because the color form has a larger absorption coefficient in the UV. On the other hand, the green emission of the fluorophore inhibits the coloration of the photochromic compounds because it induces the photobleaching of the photochrome. Experimentally, we observed that the Bisis reaction synchronizes in anti-phase condition with the photochromic compound. In fact, the excitatory UV signal, when this UV signal is strong, the fluorescence is intense and the coloration of the photochromic compound is inhibited. On the other hand, when the UV intensity decreases, the fluorescence diminishes, and the coloration intensifies. According to our simulations, we have an in-phase synchronizations between the BZ and the fluorophore, and anti-phase synchronizations between the fluorophore and the photochromic compound. What happens if two distinct photochromic compounds within the same cuvettes are receiving the excitatory UV signal sent by the BZ reaction? Well, we should expect reciprocal filter effects, since the absorption spectra of the two photochromic compounds are overlapped. We have here a spiroxazine and a benzopyran. And we obtain a recurrent network with reciprocal negative feedback actions between the two photochromic compounds. Let's assume the two photochromic compounds have the same concentrations. In this case, the strengths of the negative feedback actions depend on the absorption coefficients of both the uncolor and color forms that are all wavelength dependent. The features of the recurrent network depend on the wavelength of the excitatory UV signal. If it is 375 nanometers, where the absorption coefficients of the both uncolor and color forms for the two photograms are equivalent, then the two negative feedback actions are of the same strength and do not change in time upon excitation. If other wavelengths are selected, the recurrent network changes because the feedback actions have different strengths. This example shows that by using the wavelength dependence of the photochromic behavior, it's possible to mimic the phenomenon of neuromodulations, which is the change in neural circuits depending on the kind of stimulus received by the network. Let's move to the conclusion for these second examples. System chemistry and photochemistry are valuable to implement artificial neural models that can synchronize through UV visible signals. Our approach and our contribution to neuromorphic engineering has some limiting features. First, our artificial neural models are bulky. A breakthrough is needed, analogous to the revolution that occurred in the development of electronic computers when we moved from bulky transistors to integrated circuits and finally to microchips. Analogously, in our systems, we are moving from single cuvettes to microemulsions and nanocapsules. Second, the oscillatory reactions can work indefinitely. In time, only in open reactors. We intend to overcome this hurdle by implementing the photochemical oscillators that are based on thermally reversible photochromic compounds. Third, our artificial neural models are slow. Their periods are in the range of tens of seconds, compared to real neurons working in the milliseconds time scale, or compared to electronic components and memory resources that are used as alternative artificial neural models that work in the time range of nanoseconds. However, our goal is not to compete with the computational rate of electronic computers, but to perform other tasks that electronic computers find difficult to accomplish. Our approach has some promising features. First, the use of UV visible radiations to encode information guarantees a wealthy code for futuristic optobrain-like computing machines. Second, the use of a wetware allows having chemical communications through chemical waves, advection, and diffusion, and this is not possible in the solid state. So as general conclusion, we might ask ourselves, how and why does this research line of system chemistry and photochemistry apply to the development of chemical artificial intelligence might be valuable for reaching the goals of the 2030 agenda? Well, the answer is in different ways. First, chemical artificial intelligence can implement modules for chemical robots that will play biomedical actions. Second, chemical artificial intelligence proposes new materials and architectures to compute and new algorithms to face computational and descriptive complexities. And good results in this direction would have positive impact on economic growth. Third, trying to obtain intelligent chemical systems from scratch can help to understand what is intelligence and what is life. The appearance of life on Earth was a phase transition or sudden change in how chemical systems can process and use information. In the beginning, the world was abiotic, and any chemical matter was unable to process information. Then, about 4 billion years ago, the phase transition from a purely abiotic to biotic world occurred. What happened at the time? A deeper understanding of these emergent properties, like life and intelligence, will contribute to unveiling natural complexity from an ontological point of view. Finally, I want to acknowledge the collaborators who helped me to achieve the results I told you today. And it's also a pleasure to acknowledge my young resources and, of course, all of you for your kind attention.